Hi guys, this is my first attempt at notes for you. We're going to go over exponents today. Now some of you have already done exponents with me at school. This should be a refresher for those of you. Otherwise, this may be new stuff. We're going to go over some exponent rules and then get into some scientific notation. First off, we're going to look at what is an exponential number. 4 to the third power is an exponential number. The big number down lower is known as the base. The smaller number up above is the power or exponent. The exponent tells you how many times to multiply the base to itself. So 4 to the third power means 4 times 4 times 4. 4 to the third power. Okay, so for our first rule, we are going to look at multiplying exponential numbers with the same base. Here's our example. We're going to take 3 to the second power times 3 to the third power. So the first thing we're going to do is see what does that mean. Well, 3 to the second power means 3 times 3. And 3 to the third power means 3 times 3 times 3. So what we have now is 5 3's multiplied together. That means 1, 2, 3, 4, 5, 3 to the fifth power. So we're trying to look for a shortcut here. What is the shortcut? The shortcut is simply that you can go straight to from 3 squared times 3 to the third power to 3 to the fifth power by adding their powers. So instead of writing out all the 3's, we are just going to do 3 to the second plus the third and get 3 to the fifth power. I'm going to write down a rule for that. This is kind of my rule to help you remember. There's a more technical rule that you can look up in your book. Okay, so here's my rule when multiplying exponential numbers with the same base. You can add the powers. Some of you have already taken these notes, as I mentioned, so if you already have them, you don't need to rewrite them, but otherwise I would suggest you write them down so you can use them in the future. Okay, next rule we're going to look at is when we're dividing exponential numbers with the same base. So if we take, say, 3 to the seventh power divided by 3 to the fourth power, if we were to write these all out, the top one, the numerator here, would mean 3 times 3 times 3 times 3 times 3 times 3 times 3, 7 3's. On the bottom, we'd have 4 3's. So we could multiply those all out and divide them and see what we get, or we could look at reducing them ahead of time. So that's what I would prefer to do in this case, where we do 3 divided by 3 is 1 over 1. 3 divided by 3 is 1 over 1. 3 divided by 3 is 1 over 1, and 3 divided by 3 is 1 over 1. So what we're left with here is 3 times 3 times 3 times all these 1's, which don't change the value at all, over 1, which doesn't change the value at all. So we just have 3 to the third power. So what's the shortcut? How do we go from the division problem to the simplified answer here? If you look at it, 7 minus 4 is 3. So the shortcut here is when dividing exponential numbers with the same base, you can subtract the powers. I'm going to write that down over here, and you can too. Except that I'm always having typos. I am terrible on this new system here. Gonna try and get better. I much prefer talking to you all in person. So here we go. When dividing exponential numbers with the same base, we can subtract the powers. All right, brings up another rule or shortcut. What happens when we have an exponential number raised to an exponent? So for example, 3x squared to the third power. Well, first off, this outside third power means we've got 3 of these bases multiplied together. So that would be 3x squared times 3x squared times 3x squared. Now, if we look at some of our rules, our first rule from up above, where you multiply exponential numbers with the same base, you can add their powers. We can do the same thing here. As with, at least with the x, you can see 2 plus 2 plus 2 is 6. So we'll end up with x to the 6th power. But what about the 3's? 3 times 3 times 3 would be 3 to the 3rd power. So we went from here to here. So what's the shortcut, or what's the rule when you're taking an exponential number raised to another power? How can we skip all this part and get to the simplified answer? The rule essentially is when you have a power of a power, you can multiply their powers. So I'm going to write that down, then explain what that means for the 3 here in just a second. Okay, so there's that shortcut. Now, how does this shortcut apply to the 3 here? Well, every number, if it has an exponent or not, every number has an exponent whether you see it or not. So the x squared is easy to see, has an exponent of 2. This 3 actually has an exponent of 1. So what you're going to do is you're going to do 3 times 1 to get 3 to the 3rd power, and then you're going to do 3 times 2 to get x to the 6th power. Okay, now those rules or shortcuts lead to a couple of other unique situations that this lesson, your first remote learning lesson, is centered around, and that's 0 and negative exponents. So if we look at a simple example of, say, 5 to the 4th power divided by 5 to the 3rd power, it's pretty easy to see. 4 minus 3 is 5 to the 1st power, or just 5. Okay, but what happens if these are reversed? So let's take 5 to the 3rd power as a new example, divided by 5 to the 4th power. What happens? Well, if we do 3 minus 4, 5 to the 3 minus 4, we get 5 to the negative 1st power. So what does that mean? Well, in order to know what it really means, we need to take this in the expanded form and just kind of take a look at it. So 5 to the 3rd power could be written as 5 times 5 times 5. 5 to the 4th power could be written as 5 times 5 times 5 times 5. So if we were to divide all these 1 by 1, what would we end up with? That's 1 over 1, 1 over 1, 1 over 1. 1 times 1 times 1 is 1. 1 times 1 times 5 times 1 is 5. So what we end up with is that 5 to the negative 1st power is actually 1/5. So the rule to understand there is that negative exponents do not mean that they are negative numbers. It means that they are fractions. So 5 to the negative 1st power is equal to 1/5. So negative exponents are actually fractions. You might want to write that down. All right, that's not the technical way to say it, but it helps us understand what's going on there. One other thing to note is that if you get an answer that has a negative exponent in it, it is considered unsimplified. So I'm going to show you another example here with a variable as opposed to a whole number as our base. So let's say we take x to the third divided by x to the seventh. Well, according to our rule here, 3 minus 7 is negative 4, so we get x to the negative fourth power. And I'm not allowed to give that as my answer. According to the math world, this needs to be rewritten as its fraction value, which would be 1 over x to the fourth power, like that. So that would be the simplified answer from this problem. A couple of other examples that go along with that. If we've got, let's see here, let's say 3x to the negative second power. That is a problem you may come across. Now, big common mistake people make is they go, ooh, it's supposed to be a fraction. That must be 1 over 3x to the second power. That is incorrect. The only part that gets turned into a fraction is the x with the negative 2. This 3 has its own exponent. You could think of it as 3 to the first power times x to the negative second power. So in order to simplify this, this would be 3 to the first power times 1 over x squared. So as we finish this up, 3 times 1 is 3. 1 times x squared is x squared. So we get 3 over x squared. Now, I'm never going to go ahead and do all of this to get here. I'm just going to go straight from 3x to the negative second power. I'm just going to go, okay, that one needs to become a fraction. It's going to move down. In fact, I have a little saying that you can take or leave if it helps you. See, number one goal with negative exponents is to make them positive exponents. So I like to say, if you'd like to change the sign, cross the line. So if I were to put that over 1, you can take any number and put it over 1. And I'm going to make that positive. I just move it down here and I get 3 over x squared. And I don't even do all this writing and things, but it starts to go faster the more you practice it. Let's try, let's see here, let's try another one. I'm gonna get one from your homework. Okay, these are some examples from your classwork, not your homework, but from your classwork. I'm gonna take, this is, if you wanna look in your book, this is 872. This will be problem C, where it says 7 squared times 8 to the third power divided by 7 to the third power times 8 to the second power. Now, for this one, you can do the subtraction that we talked about. Now, you only deal with the exponential numbers that have the same base as each other. So the 7 goes with the 7, the 8 goes with the 8, and you kind of break them up into two individual problems. 7 squared divided by 7 to the third power. So we could do 2 minus 3 gives us negative 1. But if you remember what we were just talking about with the negative exponent, it's actually a fraction. We'd have to move that 7 down into the denominator. So the easier way to think about it is to think, okay, I've got 2 7s up here and I've got 3 of them up there. And as I simplify this, 2 of those would just reduce away 2 of the ones down there and leave me with 1 of them. So that would just leave me with a 7. in my denominator. Now with the 8s here, this is the same idea. This is like 3 8s multiplied together. 8 times 8 times 8. This is 8 times 8 down here. So those 2 8s would cancel out 2 of those 3 up there and just leave you with 1 of them. So that'd be 8 to the first power, or just 8. So 8 over 7 would be our answer. Looking at another one from your homework, or classwork I should say, 873 question D here. This one's a little bit longer. This one says 4x and then outside of parentheses squared times 5x squared, and they put a parentheses around it with no exponent out here, so that you don't really need the parentheses. First thing we do have to deal with is this. Remember, even though it doesn't look like it's a power of a power, these each have their own exponent. So you're going to multiply both of those times 2. So this is 4 squared times x squared, and this is times 5 times x squared. So as we go to simplify this here, the x squared and the x squared become x to the 4th power. And then this is 4 times 4. Now, if numbers are huge or have huge exponents, we don't multiply them all the way out. But if they're small like this, we can go ahead and simplify. 4 times 4 is 16, and then 16 times 5 is 80. So we get 80 x to the 4th power here. Okay, next thing I wanted to look at is 0 exponents, and how do we come across that? If we take an example here, say 5 to the 3rd power divided by 5 to the 3rd power. First off, everybody understands that any number divided by itself is 1. Or another way to think about that would have been, this is 5 times 5 times 5 on the top, 5 times 5 times 5 on the bottom. So that's 125 divided by 125, which is still 1. But what if we apply our rule where when you're dividing exponential numbers with the same base, you could subtract their powers? So this would mean that we could do 3 minus 3. So this is 5 to the 3 minus 3, which equals 5 to the 0 power. Now, the first instinct for many people is to think that anything to the 0 power is 0, but it's not. Anything to the 0 power is actually 1. Any number to the 0 power is 1. Another way to look at this is if you were to take, say, powers of 10, or any powers of any number, really. If we look at powers of 10, which is helpful as we talk about scientific notation, but 10 to the 1st power is 10. 10 to the 2nd power, okay, is this number times 10, so 100. 10 to the 3rd power is 100 times 10, or 1,000. And you guys get the idea. And the neat thing about powers of 10 is that the number of zeros in the standard form goes right along with the exponent in the exponential form. So 3 zeros, power of 3, so 10 to the 4th power, we could just have a 1 with 4 zeros, 10,000. Now, if we go the other way, just follow the pattern with me. 4, 3, 2, 1, 10 to the 0 is going to equal, look at, we've got 4 zeros, 3 zeros, 2 zeros, 1 0. So how many zeros should we have? We should have 0 zeros, so it's just a 1. Now, you could do the same thing with 2, right? So say 2 to the 4th power, that's 2 times 2 times 2 times 2 times 2, I think. So that's 16. 2 to the 3rd power, 2 times 2 times 2 is 8. 2 squared. And as we go through this, you can see as we go this way, you can just take each of these and divide by 2 to get there. So 16 divided by 2 is 8. 8 divided by 2 is 4, which makes sense for 2 squared. 4 divided by 2 for 2 to the 1st power is 2. So 2 to the 0 power, or 2 divided by 2, is going to give us 1. So no matter what number we have, so you can see 5 to the 0 is equal to 1, 10 to the 0 is equal to 1, 2 to the 0 is equal to 1. Any number to the 0 power is equal to 1. You could also continue these patterns down into the negative exponents. So say we've got 2 to the negative first power. If you divide that by 2, you get 1/2. 2 to the negative second power, that would be 1/4, or 1 over 2 squared. 2 to the negative third power, okay, is going to be 1/8, or 1 over 2 to the third power. 2 times 2 times 2 is 8. So just another way to look at the negative exponents. And the most important thing we're looking at here is 10 to the 0 power, 2 to the 0 power, 5 to the 0 power. Any number to the power of 0 is equal to 1. Okay, that should be it for the notes for this first section. I'm going to do a scientific notation notes, and that will be for your second lesson for this week, and that'll take you through the whole week. So look on Wednesday morning for my scientific notation notes, but that should be it for the exponent notes for today. This is a double lesson, by the way, so that's why there's just one assigned for the first 2 days. Same thing with the scientific notation one. It's a double lesson. It'll be assigned for the second 2 days of the week. Okay.